Find the magnetic moment of Nd3 plus ion and its ground state form. So we have to calculate for the magnetic moment of Nd3 plus ion and its ground state form. Here we are looking for two things. So before we start, we need to know the magnetic moment formula, which is mu of the J state equal G of the J state root J into bracket J plus 1 ball magneton. And we also need an expression for G. And G is going to give us 3 on 2 plus S into bracket S plus 1 minus L into bracket L plus 1 all on 2J into bracket J plus 1. So in this case, we need the value for J. The value for J and the value for S, L, and then J before we'll be able to calculate for the magnetic moment. So what element are we looking here? What element is in concern here? Nd3 plus. What's the normal electron configuration for Nd? Nd gives us xenon 4f 6s 4f4 and s2. So we are looking at Nd plus. That means for Nd plus, Nd3 plus, Nd is going to give out 3 electrons. So the 6s electron will go away and we'll subtract 1 from the 4f orbital, remaining 4f3. And now, before we get the value for S, L, and J, we have to draw the orbitals for the F. We have to draw the F orbital. So we are looking at F3, right? So, and the F orbital, it has 7 suborbitals. So 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. So after we're done with this, we start numbering 3, 2, 1, 0, minus 1, minus 2, minus 3. How many electrons we have in the F orbital? We have 3. So let's start filling singly. 1, 2, 3. So now that we are done with the F orbital, we then go ahead to calculate our S. Our S is a total spin quantum number. So we know for our spin number, if we have an orbital that is single field, that means the spin quantum number contributes plus half. But in the case that we have an orbital that is paired up, meaning we have 2 electrons in the orbital, so one of the electrons is going to contribute a spin quantum number of plus half, and the other one to also contribute a spin quantum number of minus half. So we are looking at our S, which is the total sum of the spin quantum number in the orbital that is in concern. So let's come back here. We have a total of 3 orbitals that are occupied with electrons singly. That means each orbital is going to contribute a plus half spin quantum number. So our S is going to be half plus half plus half. So this one contributes plus half, and this one also contributes plus half, and this one also contributes plus half. So we can there even go ahead and say, as far as we have 3 orbitals filled singly, it's going to give us 3 by half, which is going to give us 3 on 2. That is the value for our S. So now that we have the value for our L's, let's calculate for the value of L. L is going to give us the sum of the orbitals. I mean, we are going to add this one out to the orbital where we have our last electron. So our last electron is at 1. So we are going to add everything here up to 1. So it's going to give us 3 plus 2 plus 1. So 3 plus 2 plus 1. So this is going to give us 6. So we have our L value to be 6. Now that we have our L value, then we go ahead and calculate for the value of J. And J is going to contribute, J equal L plus S out to L minus S. Each of these has a role to play. So we know our L to be 6 and our S to be 3 on 2. So L plus S is going to give us 6 plus 3 on 2. And L minus S is going to give us 3 minus 6 minus 3 on 2. So our G will be giving us 6 plus 3 on 2 gives us 15 on 2. And 6 minus 2 on 2 gives us 9 on 2. We've gotten our J value to be 2. J has 2 values. So looking at the F orbital, if the orbital is less than half full, then we are going to take the least value for J. But if the orbital is fully half full or more, we take the biggest value for J. What is meant by an orbital is less than half full or an orbital is fully full? Let's look at a scenario here. Assuming we have an orbital like this, and we fold it 1, 2, this orbital is less than half full. Looking at this orbital, generally it's supposed to have 6 electrons in total. So if we are up to here, we can see the orbital is half filled. What about a case that we get another electron here, then the orbital is more than half full? So when we have an orbital like this, we are going to take the largest value for J. But if we have an orbital that is less than half full, we are going to take the least value for J. So let's continue. Now that we have our J values to be 15 on 2, 9 on 2, and the orbital is less than half full, we take the least value, which is 9 on 2. So our J value now is 9 on 2. Since we've gotten our J value, we can go ahead and calculate for our G. Let me transfer the work here. So we now have our J value to be 9 on 2, our L value to be 6, and then our S value to be 3 on 2. So we can go ahead and calculate for our G. And the formula for our G is here. G equal 3 on 2, 3 on 2. So G, let me write this in, right? So our G is going to give us 3 on 2 plus S, and our S is what? What about for us? 3 on 2. So 3 on 2 into bracket 3 on 2 plus 1 plus 1 plus 1, and now minus L. L is 6 into bracket 6 plus 1, all divided by 2J, and our J value is 9 on 2 multiplied by 9 on 2 into bracket J, which is 9 on 2 plus 1. Let me punch everything on my calculator. So if you punch this on your calculator, you are going to get J value to be 0.7273. So that is our J value. Now that we know the value for our G, we can go ahead and calculate our magnetic moment for Nd3 plus ion. So we know our J value, we know our J, we know our L, we know our Ls. So let's go ahead. So magnetic moment going to give us G root of J into bracket J plus 1 Bohr magneton. So now let's substitute the values in. We are going to get our G is 0.7273 root and our J value is 9 on 2. So 9 on 2 into bracket 9 on 2 plus 1 Bohr magneton. So punching this on your calculator is going to give us 3.6183 Bohr magneton. So that is the magnetic moment for Nd3 plus ion. The question is in twofold. We are to calculate for the magnetic moment and also the ground state form of Nd3 plus ion. So let's look at the ground state form for Nd3 plus ion. I want to keep these values here because we'll be needing them. So the ground state form for lanthanide is of the form L2S plus 1 and J. So that means we have to look at what is J, what is L, what is S. And from this example, from this problem, we've already calculated for our J, and we know our J to be 9 on 2, and our S to be 3 on 2. So our 2S plus 1, let's look for our 2S plus 1, is going to give us 2 multiplied by 3 on 2 plus 1. And this is going to give us 4. Yes, 4. So 2 cancel 2, 3 plus 1 giving us 4. What is the value for our G? We already knew our G to be, 9 on 2. So what does L stand for? The label L. What does it stand for? We get our L from the value of L that we already calculated, which is L here equals 6. That's where we're going to get our label here. We are going to get what our label L here stands for. So we have our L from the problem. We got our L to be equal to 6. So let's start numbering 0, 1, 2, 3, 4, 5, 6. Now S, P, D, F, G, H, I. We got for L to be 6, we got our label to be I. So now we know the value for our 2S plus 1, the value for our J. Then the ground state form for Nd3 plus is going to be I. Our 2S plus 1 gives us 4, and then our J here gives us 9 on 2. I, our 4S plus 1, 4, and then our J value to be 9 on 2. So that's it for this question. Find the magnetic moment of samarium 3 plus ion. Here we have to only find the magnetic moment, but when we are done